Hello everyone and welcome to a new episode of All Things IDA. In today's episode we're going to be discussing the PE Plus file format. We will be loading that file with no loaders whatsoever, so we'll load it in binary form and then we will see how we can manually use IDA to create the segments appropriately and dissect the PE file format as we get the database ready completely by hand. Hopefully along the way you pick up some IDA usage tips, how to express certain ideas, certain structures, and so on. I am doing this because this is a needed prerequisite for future videos. Okay, so let's get started. So the first thing I'm going to do is load the usual binary I work with Wismo64. And instead of using the actual PE loader or DOS loader, we're gonna load it completely as a binary file. This is important. We're gonna disable analysis for now and leave the loading offset and the segment at 0. By doing this, let's pick 64-bit. This is 64-bit binary, but it won't make a difference as of now anyway. So just like that, we loaded the binary file. We don't have anything useful. Everything has been loaded at virtual address 0 and file offset 0. So the virtual address and the file offset of the file have been, we're using IDA as if it's a hex editor, so to say. So what we're gonna do is create the segments appropriately, expose all the image sections and imports and so on. So we're not gonna do everything in this first video, but we will do just the beginning and continue later on. So for now, as we loaded the file, the first thing we're looking at is the MZ header. So the MZ header is the DOS header. Basically, the PE file have the DOS header and then a new header, anti-header, for example, and then optional header, followed by additional stuff such as section information and so on. In fact, Ange Albertini has nice file format visualizations. So here, for example, this is one of the nice diagrams by Ange. Just as a reference real quick. So we start with the binary and we have, the first thing is we have the DOS header, then followed by the PE header, optional headers, data directories, sections, and that's it. The rest is gonna be basically a result of describing it through those headers, essentially. Different data directory have different formats. So here, if we switch to the second annotation from Orange here, we look, for example, image data directories in the optional header has, for example, describes the exports, imports, resources, exceptions, TLS, and so on. So here, for example, if we follow the exports, we're dealing with the image export directory. The second data directory is the import. So here we have the import description and so on. So for now, before we even reach to this point, we have a few steps to do by hand. So right now, let's tackle the image DOS header. So the image DOS header is the first thing, and we need to import image DOS header into IDA. So let's do that. Since we loaded the binary file, we do not have any compiler select. So I'm gonna go to the option, select compiler, press down. And here, since the first segment is 64-bit, IDA detected is 64-bit pointer size. The default parameters look good and so on. Now, this information and other stuff happen automatically when you use an actual file loader. But for now, we want to understand what's happening and we want to do this by hand. Maybe in a future episode, we will write a file loader from scratch. But as it stands right now, we're not going to use any loaders. We're just going to use the primitives provided by IDA. So since now we are at offset 0, the first thing is the image DOS header. So to be able to do that, it's not enough just to have a compiler. I need to also import the appropriate type libraries. So I go to the type library, press insert, and I'm gonna import the Windows SDK, for example, Windows 10 x64 SDK. This is as if like we include windows.h, so this will let us import the standard structures. So now that I have the type library loaded, I will go to the structure, right click, insert, and add standard structure. And I'm gonna import image DOS header. and that's the image.dos header. So now we're ready to apply the image.dos header. We can now expand it, and we can see the DOS header information. For example, if this binary has been executed on DOS, it will not crash. It will leverage the DOS header. So let's say DOS 6.2 knows how to interpret executables, and it will find the DOS header and it will execute the DOS part out of it. Now the Windows kernel will open the executable and leverage the ELFA new field, which points to the new header that either it's a new executable for Windows 3.1 or the PE header, for example, which could be for different architectures as well, not just say x86, x64, and so on. So having done that, we can observe a bunch of things. For example, the code segment, instruction pointer, that's like the entry point. If there are overlays, and so on. So these used to have meaning in the DOS days. We will explore this as well as we go along. Now that we have loaded the DOS header, let's follow the ELFA new to the offset E8. Since we loaded the file as binary file at base 0 and so on, we don't have to use the jump to physical file offset because this is physical file offset. The ELFA new is a physical file offset. We can use just jump to address. It's going to be the same. So we can go to F8, and this is where we now need to apply image NT headers, which basically we can see it after the DOS header here. After the image DOS header, we have ELFA new pointing to the PE header. And we can also see it in the actual MSDN documentation. The DOS header and then the actual PE header, COP file header, and so on after the signature. So we know what we need. We need to import image NT headers 64-bit version. So let's go back to structures and insert, add standard structure, and type image NT headers 64. And apply. We have it now in the structures window, so we can go back to the disassembly view, press Alt Q, and apply it. So we're gonna apply image NT headers. And here we have the PE signature, machine, number of sections. So these are image section headers, timestamp, and so on. I'm gonna basically copy some nice information that will be handy. So for example, image base. Let's copy image base. And we're gonna deal with those data directories later on. And let's see as well what could be useful. For example, we'll talk a bit about section alignment, file alignment. These are also important fields. Number of sections, just as well to discuss it. Okay, so I think this should be enough for now. So if we go to the image NT header as it stands, we have the PE signature, we have a file header containing a bunch of fields. It's just 14 bytes hex in size, and then the optional header containing more information plus the data directories. So the image file header has machine spec, number of section, characteristics of the PE file, and the optional header has more stuff. For example, linker information, image base, file alignment. So how the actual section contents are aligned on disk versus the other alignment in memory alignment. So we have two different alignments, file alignment and section alignment in memory. And the data directories, they are fixed size, 16 directories altogether. And since this is made as an array, it might not necessarily be as useful as it is like this. So we might want to break it into the individual data directories. And we should see like the indices. So for example, here we have the data directories of form image data directory as we see. Image data directory, and it says among those 16 we have, for example, the first one is data directory describing export table, import table, resources, debug, TLS, and other stuff basically. So it depends how deep we want to explore the PE file format. We can explore different things. We're not gonna cover everything today. Okay, so now let's tackle, after the image NT header, we have the series of sections, and we did note that we have number of sections 7. So let's bring in the image section header if it's not available. So let's see here, I don't have image section header structure, so let's add image section header. Okay, And that's the image section header. Let's apply it. So after the image NT header, which we are, this whole block, this is where we have the section header. So that looks like the section name and so on. Let's press Alt Q and apply image section header. And that's the first section. What we need is actually to make an array, press star and apply 7 of them because we have 7 in the file description. So here we have 7 sections, and then the rest is just padding basically to allow the alignment to happen on this. So the actual PE file has on disk alignment so that the file system driver is accessing the file in an optimal manner. So sections will be really at nice boundaries. We noticed, let's see here, 200 hex, so that's 512 sector size. So this plays well with the disk driver or the file system driver. So these are like just for optimization and so on to have best performance. The PE file will not be jammed in at odd addresses and so on. So it's important to know the alignment. Let's just make this a bit clean, the section here, and press A to make it look like a string. So I pressed A in the name just to make it render as like that. Having done that now, we should be able to start creating the sections correctly. So far we read the file, it's mapped at 0 and nothing really is that's not how the operating system maps it to memory and executes it. But just to take a peek, for example, this is the text section. If we look at the image section headers, we have some information. So if you look, we have the name of the section, then we have some union field here. Either it's the physical address or virtual size. It's a union. The virtual address, that's where the RVA, the relative virtual address from the image base, where that section will be loaded. So that's important, but this is the virtual address in memory. We should have a pointer to raw data. That's the physical offset. So let's take a look at the physical offset. So we have two, size of raw data and pointer to raw data, describing where they are in on disk. And since we mapped this database at offset 0 with no virtual memory or anything, this is like a hex editor. So right now, if I pick the pointer to raw data value for the .text, and just go to 400 hex, it will take me to the beginning of the text section. So let's try. But first, I'm going to copy all those as well, just for reference, put them in my scratch pad. And let's jump to 400. So let's jump to 400. And here, if you recognize these opcodes, this is the beginning of the text section. So as a first step, what I'm going to do is just create segments, still map them at the physical offsets. I'm not gonna map them virtually yet. I'm just gonna segment the database while retaining the physical offsets, and then I'm gonna move the segments accordingly. So we'll do this like in 2 steps and start by creating the segment for the text. So let's rename that segment to header, Alt S, and type header. Now this header segment is everything, is the whole binary, but we want to break it down into individual segments mapped at physical offsets for now. And then I'm actually show you how we can adjust them to really map as if the OS loaded them into the virtual memory space. So let's go and to the pointer to the raw data. So G and 400. I'm gonna press Alt L to begin selection, and here we have size of raw data. That's how much bytes we have on disk. Now we might have size of raw data 0. I'm not sure if we have it in this case, like for uninitialized sections like BSS and so on. It might only have virtual size, and that means it doesn't have any physical backing. It's just gonna cause the operating system to allocate virtual memory and say initialize it with 0 with the given virtual size. But for now we have physical size. So I'm gonna jump, press G here, selection is enabled. G plus, so from here I'm gonna jump to size of raw data, so 15600, and this is the range of the text section. So I'm gonna say edit segment create. I'm gonna leave everything as is, just call it .text for now and give it code class. Remember when I loaded the file, I had analysis disabled. I don't want either to analyze as of now. I first want to set up the database and point it to where it needs to start analyzing. So that's the first text section. And we can see the only difference really is we split the whole, it was a single segment. Now we split it into actual header, which is 400 hex, and then the text section. And these are physical offsets as of now. And then the remainder as well. So header got split into two parts, basically. Once it's split, we introduced the text, then text got inserted in between, and now we have header split into those two, before text and after text. So this one we keep splitting, and get rid of it, because these are the actual body of the file. They're not part of the header. So header really here, the third entry here, is just the dummy name. So now we have the text. Let's go do our data. Physical pointer to raw data is this one. So I'm gonna jump to that. This happens directly after. So let's just begin selection, Alt L, and go to size of raw data. So go to plus AE 0, 0. And edit segment create dot R data. Keep the same physical boundaries and press OK. Now this gives me an opportunity to discuss a bit about some attributes in the image section. And because if we edit the segment as of now, I don't have proper permissions, and it would be nice to have some proper permissions, but I cannot just make up the permissions. So I want to respect the header, and we have that information from the characteristic field of the image section header structure. Let's try to render this in a nice way so we can map the image section characteristics to something that we can read in IDA and partially express in IDA. What that means is when we look in the documentation, let's see if we can find it here. So the characteristics of a section are constants that start with like image scn. So for example, it will tell us if it's image scn, mem execute, mem read, and so on and so on. These play a big role as well, how the actual virtual memory of the PE file is allocated and protected and so on. Like we see here, shared, for example, that will cause one of our virtual memory of a section, for example, to be accessible from other processes, for example, like a memory mapped file. So now let's jump back to the header, to the PE header, and I'm gonna make a bookmark actually. So let's just bookmark the beginning of sections here. Sections. Okay, so what I want is to have something nice out of the characteristic. So really I want to create an enum containing all the image scn stuff. Let's see if we can import them directly from IDA, since we have the type information loaded correctly. So we can open the enums window, press insert, and add standard symbols. So I'm gonna add standard symbol. IDA, because we loaded type information library for MS SDK 64, recognizes 187,000 enum constants parsed from the Windows SDK. So we should find one of those. So all I'm looking is a single constant and hoping that IDA managed to group all of those related constants and bring them as an enum. So let's see, image scn, for example, mem execute. Let's see what we got here. So I open it up and it feels I got a lot more than I want. Like image sim definitely belong to another category and so on. I only want the image scn constants. So eventually here, if we look, we have them, but we have more than stuff. So a quick way as well we can deal with that is let's open the local types window, edit this. I'm gonna just temporarily put it in some file real quick and filter it. So let me filter it, go to the prompt and just grab a bit. So here type and find string image scn, and let's take it back to clipboard and paste it here. So like this, I filtered all the scn strings out of the whole thing, which had more than just scn stuff. And another thing is the scn flags are ORed together. So we can have a combination of flags. That means in IDA, if I want to see an image scn, for example, that is a combination of flags, like here definitely is a combination of two flags, let's say 4 and 2, for example, and so on. We need to have a bit field in the enum window. So I'm gonna Control N on this one. First, let's call it scn, just change the name. And if I change it to bit field as it stands, it will not work. And I will explain why. And already we can see problems like this value here is not a power of 2. So if we want to enable bit field, we have to have all the values in the enum to be power powers of 2. So here we did get some error and we have to clean it up. So what I'm going to do is just quickly scroll through those and find the values that are not power of 2 and remove them. So I'm just press U, that deletes the enum member. So this one, 6, 7, 9, A, B, C, D, E, F. Let's see, maybe I missed something here. I only keep the power of 2's. So here 3000. Let's try again, Control N, bit field, enter. Great, now it works. So now we can use this as an actual specific operand type. And let's then use that enum in the struct window in the image section header, characteristics. We can press M to change that to image SCN macros. So here M, yes, and that's one candidate. So we selected. So now the characteristics is no longer just a regular number. It's actually a number, but it has constant representation, and that will reflect into the database. So now look at this. We have we got rid of those magic numbers, and we can see that for the text section, it's code, execute, and read. So that's good. For example, our data says we have initialized data and read only, and we can see our data. For data, we should expect initialized, read, and write. If you want to patch a binary on disk and make certain sections read, write, execute, you have to patch the characteristics field of that section. And by doing that, when that PE file is executed, its section will be writable as well. So that's how basically we can also patch and understand what we're doing when we are manipulating PE files and so on. And a good way really to play with those fields and so on is using hue, as I showed you in a previous video. So far we have created text and our data. So we're not done yet. We're gonna do the rest. It's gonna be the same story, but I might skip ahead. If I now look at what we did so far, we have to do more stuff, but what we did is I simply broke the binary file that I loaded as a big chunk and then parsed the headers, figured out how many sections, figured out information about the sections. We haven't fully consumed all the information, and all I did really is simply do physical segmentation, not virtual memory. I didn't really split it to be looking how it would look like in the physical memory. So we will now go and apply the proper segment permissions from the SCN, and we'll also have the individual sections to be loaded correctly into their proper virtual addresses. I did this in steps just to make it easy to explain. So now we can look here, the address of text pointed to raw data is 400, which is what we see here. That's the physical offset, this is a virtual address. But in reality, we do have that binary would like to be at virtual address 1000. And this is relative address. And remember, we took the image base earlier here from the optional header field. So this is going to be important as we start to realign those segments correctly into virtual memory layout. So for the .text, let me recopy those with the proper permissions that we applied and update stuff cleanly. So let's jump to text and move that segment. First, let's edit it. So we can see here it has SCN code, execute, and read. So Alt-S first to just edit the segment, and editing the start and end is not gonna help us because we wanna move the contents as well, not just like the logical boundaries of the segment. We wanna move the segment and its contents. But for now I edited just to make sure I have proper bitness. So let's say I was loading a regular, not a PE plus, but just a PE file, 32 bits. Maybe I would have edited the segment to selected 32 bits. Here I have to apply execute that maps to code. That's just the permission. So not everything we have in all different file formats, one-to-one mapping in IDA. So IDA tries to be generic to accommodate for multiple formats. And that will help the decompiler as well reason correctly about things, because if we don't have proper permissions on the segment, let's say we have non-execute permission, the decompiler can decide that this is data, why should I decompile it, for example. So now let's move the segment, edit segment and move. So where do I need to move it to? We need to move it to the image base plus the virtual address. So let's move it. We're now trying to break free from the physical offset mapping and go to virtual address mapping. So the image base plus the virtual address from the section information we got here that's where we want to move. Now, fix up the relocated segment is not going to be useful since IDA doesn't even have any notation or understanding of fix ups because we loaded it as a binary. So this is a no op anyway. So for now, that's good. Now, if you press Ctrl S to look at what we've done so far, we can see it's starting to shape up. We have the dot text. So let's continue. We have text. Let's go and move our data. Edit, edit segment move, and we're gonna move this one to the image base plus the the relative address. So here, this is the base plus the virtual address. I'll press OK. And now we have .text.our data. We'll do the same for data virtual address, edit segment move. Let's quickly do it. So now as well, let's edit the segment and make it read write. So here, read write. See what I did with our data, maybe I didn't apply it, so only read. So you just keep it read. Now p data as well. P data is that's the virtual address. So let's edit segment move. We're gonna move it off the image base plus the relative address to give it full virtual address that we can see in IDA. So now in IDA, that section is at image base plus the actual desired virtual address per the image section on disk specification, and we need it to be only read. So let's edit the segment, make it read. Now when it comes to the bitness of data, it won't make a big difference. It will make a difference for code because that will affect the decoding. So if we are dealing with the .text, for example, and we choose the wrong bitness and disassemble, either we disassemble per the bitness of the segment. So far we'll have towards the end, I'm gonna go and create this DOS header and show you how it makes a difference. So now let's do the our data virtual address is here. So edit segment move, and let's do okay, let's apply the permissions as well as just read. By the way, as well, I forgot to, as I edit, put the classes, and classes make a difference as well. So for example, here for the .text, I think I did put code, this one data, this one data. Okay, so let's go for resources. That's the virtual address. Edit segment move. And let's do the relocation. As well, let me edit it. So resources as well as read only. And finally, a relog, edit segment move. And this is the relative virtual address, and that gives us the full. And so we can't map discardable, for example, but we can definitely map just the read part here. And here we have that. We're not done yet. We have still the header, and I'm gonna extract the DOS header for this video. Now, as you know, the header is not mapped at memory 0, and when we loaded the file as binary file, we loaded everything at 0, but now we moved certain parts, but we still have to move the header, and the header should be at the image base. So when we load a PE file in memory, we go to the image base, we see the DOS header, and that's what we're gonna do. So we're gonna simply move that segment from physical offset 0. It will keep its physical backing at physical offset 0, but visually in IDA we wanna show it at the image base. So I'm gonna edit segment move and just put it at the image base. That's it. And press OK. So now the header is fine. The header is read only, and let's just make it read only. Okay. We can do a bit more. There is more stuff to interpret and understand in database, but this video is already long, so we're gonna wrap it up by simply extracting the DOS header, and we continue later on. When it comes to the DOS part of this, after the image DOS header, which has 40 hex, we have the actual code. So after this, here, let's see if we can hide this. And this subsequent stuff, this is the potential 16-bit code. But where does it start? Here it's just saying that basically the segment is 0, IP is 0. So this is basically, we need to map this as 0. So let's do that. So first thing, as usual, I'm gonna split that segment by making the selection I want to extract out. So header already right now contains the DOS part. So I'm just gonna select, and so the header contains DOS header, DOS code, ImageNT headers, the section. The first memory page contains all the headers, including the DOS stub. But what I'm doing right now is just simply extracting out its own segment containing the DOS code. So I just selected, past the MZ header, I selected the DOS code basically, and I stopped up to the PE header. I'm just gonna separate it, so just made the selection, create a segment, and fine, as it is for now, let's keep it. So like this, what I did as well, instead of having header continuously from the base all the way to the end of the headers and followed by the sections, I just simply broke it in pieces. If we are actually gonna be looking at on disk, what I really did, this is the header, and here we have the DOS program here. So I took that part and made its own segment. This is the PE header and so on. I kept them. But what I want to do is I want to simulate the execution environment. So if we are running this program under DOS and we put it under a debugger, we will see that code executing in a certain virtual memory address. And I want to show that in IDA similarly. And by the way, what I'm doing here, I'm taking a lot more than I need. I took this and up to the PE header, and here there's like some what's it called, rich header. So let's just ignore this, and I will just make it part of the DOS header. It doesn't matter really, it will not change anything, and we can always move them around. So now that I simply split that DOS segment, this is DOS program, I called it DOS. But this is not really where it's gonna be executed. It's gonna be executing at CS0, CS IP 00. So all I have to do is simply move that segment to 0. Edit, segment, move, and let's move it to virtual address 0. So we can still see the physical offset is at 40. That's correct. This is where the bytes are actually on disk. But in virtual memory, the address is 0, and this is very important because as we disassemble the code, we'll see references and offsets, and if we don't map it at 0, they will point to some weird locations. Now, let's take a look at the segment, Alt-S, and here I kept it 64 bits. And so I did this on purpose to show you that now if I try to make code pressing C, I can't, because apparently under 16-bit mode, I cannot disassemble 0E. So here, for example, if I go to Hue, we are in 64-bit mode, PE+. I'm going to edit the file and type 0E. Already I have undefined instructions. So this is what I'm saying with respect to the mode. But instead, if I switch modes to 16-bit mode, then if I type 0E, it starts to disassemble correctly. We see push CS and so on. So that's what we're going to do with respect to IDA. We're going to edit the segment and change it to the proper bitness so that when we disassemble, it disassembles correctly. Are you sure? Because if we do that, it will destroy whatever you have worked with. It will change the item sizes and so on. Since we haven't done anything yet, it's fine. Now the addresses and the IDA's display is 16-bit and so on. We can start to make code. So I'm just going to make code. Okay. And the reason I had made a selection because I still kept analysis off. So as long as analysis off, if I make code, so I'm going to undo. If I make code, it will make code once. And then I have to make code again. I don't want to enable analysis yet. So I want IDA to wait a bit, and then I will enable once I add the actual entry point and have IDA to work with. But even if I do that, it's still not gonna be enough because we still need maybe to map the imports and all important information. So IDA does a better job at analysis. But if we stop here, first, before, let's just make the code again and just analyze it. So what happens when we run this program under pure DOS? What happens is it will just assign the data segment. So this is segmented program. So they're putting ds is cs, and then they want to display a message, function 9, calling DOS interrupt. It displays the DOS strings and dollar terminated. And that's the offset. And since CS and DS now is CS, you can see here E is actually pointing here, which is the program, the string. So edit strings and DOS string, dollar terminated. And now I can go here, press Control O, for example, and see they're calling DOS interrupt 9, function 9, print a dollar terminated string, and the string is at dsdx, and ds is cs, so it's in the same segment, and that's what they're printing. So this program cannot be run in DOS. And then they're calling for C, which is terminate program with exit code 1, then issue interrupt 21, the DOS interrupt. And simply that's DOS stub. Does not cause a crash. You run a PE file under DOS, it will display that message nicely and terminate. Let's go and figure out the entry point. So the entry point should be somewhere here, address of entry point. Let's also just put it here on the side. So we took the entry point, which is this, which is a relative address. So let's now, it's relative from the image base. So if we go to header, so let's get rid of this. So this is the actual DOS header. When we split it, so let's see, okay, we can call this PE header, for example. So we have DOS header, a DOS program, let's call this DOS stub, stub. This is the whole header, let's just keep it header. This is the PE header, and these are all the individual sections. So going to the header, which is the base, image base, jump plus the RVA to the entry point. This is the actual entry point at 1400 1B20. Let's switch to Hue real quick. Go to the header hex view, F8 for the headers, and F5 to jump to the entry point. So F5, and the entry point is exactly the same. We can see 488. This is the entry point. So here is the entry point. We can make code and so on. But before we do that, again, if I do that right now, enable analysis, either will analyze as much as it can, but we don't have imports yet. We still have to, in the next video, go and look for the import directory and parse it, rename the locations of IAT entries and so on. So IDA can track arguments and have better analysis. This is the entry point. I'm gonna use a function called add entry, and that will let me programmatically insert an entry point. So add entry point, let's say ordinal is its index in the list, EA, so we can use here. And the name, usually the loaders calls them start, make code, yeah, flags keeps them 0. And now if I press Ctrl E to jump to entry points, I have simulated an entry point here. We're far from done, but it should be enough for now. I'm gonna let it analyze and just show you how it works, and later we'll continue and see how it will be better. But let's see how far we go with what we've done from scratch. So let's enable, and okay, good enough. We don't have imports, we don't have much stuff. So if I follow here, for example, these D word pointers are actually gonna be filled from the import table. And we're not there yet, but we will also go interpret that and rename them to all the APIs and so on. But as you can see, the disassembly went smooth. Illumina detected some patterns and so on. We can do one more step, go to the signatures, Shift F5, insert, and we can say VC64 RTF. This is for the runtime, 64-bit runtime for a Visual C++ program. So I know Wizmo has been compiled with Visual Studio. This should give us library functions. So let's see what this gets us. So it gave us 52 library functions. So let's open the functions window and try to sort by, this is library function. Let's see, let's sort them like that. So just to see what we got. So it found the security cookie, looks correct to me. at exit, and so on. Like just like that, completely manually, we achieved a lot. Of course, we have more things. So we still have to parse relocation. We will have to parse our data. And so we have to feed the relocation into IDA as well. So IDA knows how to fix up things if we rebase the program and so on. P data. And we'll see what else in the next episode. So that's it for today. I hope you found this video useful. We covered how to do things completely manually in efforts to understand the PE file structure. If you really enjoyed that topic and you want to learn more, the best way is to pick a binary and repeat those steps at your own pace to have a deeper understanding of PE file formats. So I'll see you in the next video for continuing this series. Thank you and see you next time.